You know when you look at a stock chart or maybe some weather data and it just looks like complete and utter chaos? Well, what if I told you that hidden inside all of that noise, there are patterns, a kind of memory, where the past is constantly whispering to the present? Today, we're going to learn how to decode that memory and actually listen to what it's telling us.
So, first things first, let's talk about what makes this kind of data with a memory, so unique and honestly so tricky to get a handle on sometimes.
Just take a look at these two charts. On the left, you've got Google's stock price. Pretty clear story, right? It's generally heading up. But then look at the chart on the right. That's the daily return of the US dollar index. And it looks more like random static, just bouncing all over the place around zero. They both tell a story over time, but their behaviors couldn't be more different. So where do you even start trying to make sense of either one?
Yeah, that dollar index chart really does look like a bunch of random noise, but I promise you it's not. There's a hidden structure in there, and the key to unlocking it is this question right here. What if this data has a memory? What if what happened yesterday, or even last week, directly impacts what's happening right now?
And that's the absolute heart of the matter. You know, unlike flipping a coin, where every single toss is a completely fresh start, these data points are connected. They're linked through time. Today's stock price is deeply, deeply connected to yesterday's price. And that connection, it breaks one of the biggest rules in a lot of standard statistics. And that's the puzzle we're here to solve.
So, how in the world do we deal with data where the past is always messing with the present? Well, we need a special tool, one that's designed for exactly this. We're going to borrow it from the world of probability, and it's all about playing a little game of what if.
And that powerful tool is called conditional probability. Now, the official definition is right there. It's the probability of event A happening given that event B has already happened. And in that P of A/B notation, that little vertical bar is the key. You can literally just read it as the word given.
But let's just cut through the jargon for a second. All conditional probability really does is answer a very simple but incredibly powerful question. How does new information change the odds? If I tell you something new, how does that affect your guess about what's going to happen next?
All right, let's make this real. Forget stocks for a minute. Let's talk about something way more important. Cookies. Imagine we have a jar with 20 cookies, and this table shows the breakdown. If I just ask you, hey, what's the chance of picking a cookie with nuts? You'd look at the totals and say, well, there are 12 with nuts out of 20 total. Easy. But what if I give you a clue? What if I tell you the cookie you just picked is dark chocolate?
See, the whole game just changed. We're not looking at all 20 cookies anymore. That new information, the condition that it's a dark chocolate cookie, shrinks our entire universe of possibilities, what statisticians call the sample space. Now we're only looking at those 9 dark chocolate cookies, and in that little world, the chance of getting one with nuts is now 6 out of 9. Our new information completely changed the odds. That's conditional probability in a nutshell.
Okay, the cookie detour was fun, but let's bring this powerful idea back to our time series data. We can now use this what-if thinking to start measuring that data's memory, or as I like to call them, the echoes of the past.
So the question we're trying to answer becomes this. How can we measure the echo of the past on the present? How strong is the echo from a data point, say 3 days ago, on the value we're seeing today? Is it a loud, booming echo, or is it pretty much faded away into silence?
The tool we use for this is called autocorrelation, or just ACF for short. It basically gives us a number that tells us how related today's value is to a past value. We call those past values lags. So the ACF at lag 1 measures the connection with yesterday. Lag 2 is the day before that, lag 3 the day before that, and you get the idea.
Now, here is the absolutely crucial thing to understand about ACF. It measures the total relationship. So if we're looking at the echo from 3 days ago, ACF doesn't just measure the direct link. It measures the whole chain reaction. How 3 days ago influenced 2 days ago, which influenced yesterday, which influenced today. It bundles all of that indirect, knock-on stuff together into one single measurement.
But, bundling everything together like that can be a little messy. It tells us there's an echo, sure, but it doesn't tell us exactly where it's coming from. So what if we want to be a bit more precise? What if we want to isolate just one single direct link in that chain? So that leads us to a much more surgical question. How can we measure the pure, direct relationship between today and, say, 3 days ago, after we've already accounted for the influence of yesterday and the day before? How do we cut out the noise from the middlemen?
And for that, we've got our next tool, partial autocorrelation, or PACF. And just look at that definition. See that phrase, conditional correlation? This is where our cookie example comes roaring back. The PACF uses that same logic to measure the direct link between 2 points in time, after it's stripped out all the effects of the points in between.
This slide really nails the difference. Think of it like this. Autocorrelation, the ACF, measures the total influence. It's like hearing a loud echo of the past that's been bouncing off all the walls. But partial autocorrelation, the PACF, isolates just the direct influence. It's like hearing a clean, crisp whisper directly from one specific moment in the past, with all the other noise filtered out.
Okay, so now we have our decoder rings, the echo-detecting ACF and the whisper-detecting PACF. Now for the really fun part. Let's apply these tools to our data and finally reveal those hidden patterns we talked about at the very beginning.
And we're back where we started, looking at the Google stock price. At first, it just looked like a line going up, but we knew there had to be a more complex memory structure hiding under the surface. And now, we have the exact tools we need to see it. So first, let's look at the autocorrelation plot for the Google stock data. Each of these vertical bars shows you how strong the echo is from a past day. And just look at that pattern. See how the bars start really high, and then they just slowly decay over time? That right there is the classic visual fingerprint of a strong, persistent trend. It's telling us the echo from yesterday is huge, and the echo from the day before is still huge. The memory is long.
Okay, now for the PACF, our whisper detector. And whoa, look at this. It's a completely different story. We've got one massive spike at lag 1, and then everything else just drops off into nothing. So what's that telling us? It's saying that once you know yesterday's price, the prices from 2 or 3 or 10 days ago, they don't really add any new direct information. The only whisper that matters is from the day right before.
So you see what we just did? By using these two plots together, we've basically found the unique fingerprint of this data. The slow-fading ACF, our echo detector, told us there's a strong trend. And the single spike PACF, our whisper detector, told us that trend is almost entirely driven by a powerful day-to-day relationship. We just turned what looked like a simple line into a rich, detailed story about its memory. So let's just do a quick recap of the journey we took. We started with a problem: how to make sense of this weird data that remembers things. We found our key, which was conditional probability. We used that key to build our tools, the ACF and PACF. And then applying those tools led to the big payoff. We can actually see the data's memory.
And all of this leaves us with one last big thought. We've just seen how we can use these echoes and whispers to get a clear picture of the past. And that is the absolute first step towards building models that can predict what's next. So the real question becomes, if we can learn to decode the memory of the past this clearly, what can it truly tell us about the future?